December 27th, 5:42 in the morning, Greenland local time. A crack that had been spreading without anyone noticing for months finally hit its limit along the northern face of Jakobshavn Glacier. In under 4 minutes, a section of ice 3 miles across, half a mile deep, and taller than a 60-floor skyscraper tore free from the glacier wall and dropped into Disco Bay. The nearest research outpost heard it like an explosion. What followed was something else. Seismic stations across Greenland, Iceland, and Canada all picked up the signal at the same moment. Not as an earthquake, as something outside every known category. The readings were sharper, quicker, and more violent than anything a standard calving event had ever produced. Scientists at the Danish Meteorological Institute looked at their screens and found nothing in the reference library that matched what they were seeing. 6 minutes after the ice hit the water, automated detection buoys scattered across the North Atlantic started sending out alarms. The wave measured at the source stood at 58 feet. That is not a freak ocean swell. That is a vertical wall of moving water traveling at freeway speeds across open sea. As it pushed south and east, it flattened out but widened, stretching across an arc of ocean that put Iceland's western shore, the northern edge of Newfoundland, and Greenland's own villages directly in its way. Iceland's Civil Protection Agency issued coastal evacuation orders at 6:09 in the morning, 27 minutes after the collapse. In the fishing town of Stikisholmur on Iceland's Snæfellsnes Peninsula, the harbor master was already moving boats before the alert reached him. He had felt something off before any siren activated, a strange calm in the water, a pulling sensation like the bay was drawing a breath inward. In the Greenlandic settlement of Catastrophic, sitting just 40 miles from the collapse point, there was no 27-minute window. Residents had a matter of minutes. A Coast Guard helicopter pilot was in the air within 8 minutes of the first alert, trying to coordinate evacuations across a radio channel jammed with voices. From above, she could already see the harbor changing color as the first surge pushed into shore. Across every affected coastline, rescue teams pulled more than 2,100 people from immediate danger areas within the first 3 hours. 14 coastal buildings were destroyed or heavily damaged. 3 fishing vessels went to the bottom inside their own harbors. The financial damage to towns built entirely around ocean access was instant and absolute. By the time the wave energy finally scattered across the mid-Atlantic, 47 separate monitoring stations in 6 countries had logged the event. Every single one of them had captured something their engineers had never designed them to see. Jakobshavn Glacier did not break without warning. It broke after decades of warnings that went unheeded. Greenland's ice sheet is the second largest frozen mass on the planet. The water locked inside it, if released entirely, would lift global sea levels by 23 feet. Not a few inches, not a foot or two, 23 feet. That single number would completely redraw every coastline that exists, drowning Miami, Amsterdam, Shanghai, and dozens of other cities before any evacuation strategy could be put into motion. Jakobshavn is Greenland's fastest-moving glacier. It has been pulling back inland at an increasing pace since the early 1990s. In 1990, it was retreating roughly 20 meters a year at its forward edge. By 2023, that figure had climbed past 40 meters annually. The glacier was not simply shrinking, it was accelerating toward open water, as though something had cut the brakes. The process driving that acceleration happens below the surface. Warm Atlantic water, pushed northward by shifting ocean circulation, had been boring underneath Jakobshavn's submerged base for years. This is called submarine melting. It hollows the glacier out from below, carving invisible chambers that no satellite can fully see. The ice above still looks solid. Underneath, it is emptied out. Scientists at the National Snow and Ice Data Center in Boulder flagged the escalating submarine melt activity at Jakobshavn as far back as 2015. Their papers called for better monitoring. The funding was never approved. A researcher at NASA's Jet Propulsion Laboratory had been measuring the ocean temperature readings feeding into Jakobshavn's base for 4 full years before the collapse. The water arriving at the glacier's underside was reading 2.7 degrees Celsius above the regional historical average. That sounds minor. At the boundary between ice and seawater, a single degree of warming can double the rate of melting. 2.7 degrees was not minor. It was catastrophic. The concept researchers feared most was marine ice cliff instability. When a glacier pulls back past a certain water depth, the exposed face of ice grows too tall to hold itself upright. It does not melt away slowly. It falls apart mechanically in sections. Each section that drops exposes a fresh face that is equally unstable. The process feeds itself. Each failure accelerates the next one. A scientist at the National Snow and Ice Data Center described Jakobshavn in a 2023 research brief as a glacier that had already passed the threshold for stable behavior. Her language was measured and careful and almost entirely overlooked outside the academic world. The glacier continued moving regardless. The instruments did not deceive anyone. They simply told a story that no one had built a category for. Within seconds of the collapse, seismic networks across the North Atlantic began logging a signal that did not fit any standard classification. Earthquake software rejected it. Volcanic protocols did not apply. What sensors recorded was a hybrid, part mechanical fracture, part hydrodynamic collision, a seismic signature that had never been formally documented at this scale from a glacial source. Researchers at the University of Copenhagen flagged the anomaly within 11 minutes and immediately started pulling archived records to find any comparable historical event. There was nothing. Underwater microphone networks originally constructed to track nuclear tests during the Cold War detected the collapse across more than 2,000 miles. The acoustic signal moved through the ocean at speeds precise enough for monitoring stations in Iceland, Norway, and the northeastern United States to time the event to the second. What caught analysts off guard was not how loud the signal was. It was how long it lasted. The collapse did not produce a single impact. It produced a cascading chain of fracture events spread across nearly 4 minutes, indicating that the ice face had not fallen as a single unit, but as a sequence of connected failures, each one triggering the next. Satellite images from the European Space Agency's Sentinel-2 system showed before and after frames that captured the scale of destruction without any ambiguity. A fracture line visible in orbital imagery for 7 months had torn along its entire length in under 5 minutes. Glaciologists measured the newly exposed ice face at 312 feet above the waterline, with an estimated 900 feet of glacier remaining beneath the surface. That geometry placed it squarely within the marine ice cliff instability range that researchers had modeled but never watched happen live. Ocean temperature sensors at the glacier's submerged base recorded a spike at the moment of collapse. Cold meltwater that had been pooled inside the subglacial cavity surged outward and upward, creating a thermal pulse that confused the nearest tsunami buoy's wave origin algorithm. The buoy was built to read earthquake-generated tsunamis, which behave in a fundamentally different pattern. It initially underreported wave height by 34%. That error directly affected evacuation timing for 3 coastal communities. A scientist at the University at Buffalo reviewed the full sensor data set within 48 hours. Her conclusion was unambiguous. Every projection model used to forecast Jakobshavn's behavior had underestimated the speed of structural failure by a margin that could no longer be written off as natural variability. The glacier had not broken the laws of physics. It had broken the boundaries of assumption. And those assumptions, she noted, were still embedded in every coastal risk framework currently driving international policy. The wave did not care about evacuation timelines or alert infrastructure. It moved at the speed it wanted and arrived when physics said it would. In Qeqertarsuaq, a Greenlandic community of roughly 800 people sitting 40 miles from the collapse point, the first sign was not an alarm, it was the harbor. A fisherman who had spent 22 years working that coastline noticed the water pulling away from the dock in a way he had never seen before. The bay was draining. He ran. He was already 300 feet uphill when the first surge came in, lifting his boat out of the harbor and dropping it onto the main coastal road. He watched from high ground as the waterfront his community had built over generations disappeared beneath 6 feet of churning gray water. The town lost its harbor master facility, its primary fish processing plant, and 14 of its 31 registered vessels. For a community whose economy runs entirely on what comes out of the sea, those figures do not represent property damage. They represent the erasure of a livelihood, at minimum temporarily, and for some families permanently. In Stykkishólmur, Iceland, the 27-minute warning sounds reasonable until you understand the layout of the land. One road runs out of the low-lying harbor area. Under normal conditions, it manages daily town traffic without difficulty. During a simultaneous evacuation of 200 residents, it became a single gridlocked lane within 6 minutes. A Coast Guard officer directed traffic at the main junction alone for 19 minutes while water climbed the road behind her. Everyone in her section got out. 2 elderly residents in a separate district, unreachable by road before the surge arrived, were lifted from a rooftop by helicopter 4 hours later, cold and shaken, still breathing. Emergency shelters across Iceland's western coast were holding 3,400 displaced residents by nightfall. Aid organizations reported acute shortages of dry clothes, baby supplies, and medications for chronic conditions within the first 12 hours. Delivery trucks could not reach 3 coastal towns due to road destruction from the surge. Helicopter drops began the following morning. In Newfoundland's remote northern settlements, the warning arrived with even less lead time. The wave had weakened but not stopped. Surges of 4 to 6 feet hit unprotected harbor areas with enough force to level 2 fuel storage depots and damage the only medical clinic serving 600 people spread across 90 miles of coastline. 41 people were injured across all affected zones. 3 remained unaccounted for a week after the event. Emergency coordinators described the survival rate as extraordinary given the warning time available. They also described it as fortunate. And fortune, as every emergency planner understands, is not infrastructure. The tsunami made the news. What came after it made researchers go silent. When a section of glacier the size of what Jakobshavn lost breaks free from an ice sheet, it does not simply create a wave. It eliminates a structural support. The collapsed ice was not floating. It was grounded against the seafloor, and its physical mass had been acting as a brake on the glacier system sitting directly behind it. With that mass removed, the upstream ice had one fewer obstacle between itself and open ocean. Within 72 hours of the collapse, sensors embedded in the glacier detected measurable acceleration in the flow rate of ice pushing toward the exposed calving front. The brake had not simply been loosened, it had been removed entirely. This is the process glaciologists call buttressing loss. Ice shelves and grounded ice margins hold back enormous volumes of land-based ice simply by being there. When they collapse, the ice behind them speeds up. When the ice speeds up, it reaches the ocean sooner. When it reaches the ocean sooner, sea levels climb faster. The relationship is straightforward. The scope of it is not. Greenland's ice sheet currently adds approximately 0.7 millimeters to global sea level every year. That figure has doubled since 2000. If Jakobshavn's accelerated flow continues and spreads to neighboring glacier systems, projections from the Potsdam Institute for Climate Impact Research suggest that Greenland's annual contribution could triple within 2 decades. Tripling 0.7 millimeters sounds small. Compounded over 20 years, added to contributions from Antarctica and from oceans expanding as they warm, it is not small at all. The tipping point concept sits at the center of every argument scientists are currently having about what the Jakobshavn collapse means in the long run. A climate tipping point is the threshold past which a system no longer requires outside pressure to keep changing. It changes itself. Feedback loops take control. A researcher at the Geological Survey of Denmark and Greenland has argued in published work that Jakobshavn may have already crossed its individual tipping point, meaning that even if global temperatures stopped rising tomorrow, this glacier would continue retreating and calving at increasing speeds for decades to come. The cities that need to pay attention are not hypothetical. Lower Manhattan sits fewer than 10 feet above current sea level. Miami's average elevation is 6 feet. London's Thames barrier was engineered for a world with lower water than current projections describe. Mumbai holds 20 million people on a peninsula where the highest ground barely clears 15 feet. These are not distant scientific abstractions. They are engineering problems that coastal infrastructure was never designed to absorb. And the deadline attached to them just moved measurably closer. The warning systems worked. That is the official position. The version shared privately among the researchers who watched the data arrive that morning is considerably more troubling. The Global Tsunami Early Warning Network was assembled in the years following the 2004 Indian Ocean disaster, which killed more than 200,000 people, largely because no detection and alert system existed across that part of the world. The infrastructure built in response is genuinely capable. thousands of seismic stations, hundreds of deep ocean pressure sensors, satellite uplinks, and national alert networks spanning dozens of countries. For earthquake-driven tsunamis, it performs well. The Jakobshavn event was not that kind of tsunami. Glacial tsunamis behave differently from seismic ones in ways that expose hard gaps in the existing detection structure. Earthquake tsunamis come from seafloor displacement across wide areas, producing long-period waves that deep ocean pressure sensors are specifically tuned to read. Glacial tsunamis come from a single concentrated impact point where ice strikes water, producing shorter-period, more disorganized wave patterns that pressure sensors frequently misread or underestimate. The 34% underestimation of initial wave height during the Jakobshavn event was not a system failure. It was the system operating precisely as it was designed to operate, but for a different type of threat entirely. A researcher at Georgia Tech has spent more than a decade documenting glacial and landslide-generated tsunamis, a category that existing international warning frameworks classify as secondary hazards rather than primary threats. His team submitted formal recommendations to the Intergovernmental Oceanographic Commission in 2021, requesting expanded sensor protocols built specifically to detect ice mass wave events along Greenland's coastline. The request was reviewed, acknowledged, and set aside pending funding decisions that were never made. The coverage gap along Greenland's western coast is not a secret inside the scientific community. Monitoring buoy density in that region is approximately 1/5 of the coverage maintained in the Pacific Tsunami Warning Zone. Communities sitting within the first 60 miles of a potential Jakobshavn-scale collapse currently have, under existing infrastructure, a realistic warning window of between 8 and 14 minutes. Coastal evacuation modeling for those same communities requires a minimum of 20 minutes for successful movement to safe ground. That gap, 6 minutes on the optimistic end, is the difference between an extraordinary survival rate and a catastrophic death count. It exists not because the engineering solution is out of reach, but because the political commitment to fund it never materialized. A U.S. senator raised the monitoring shortfall in a Senate Commerce Committee session 3 weeks after the event. The Department of Homeland Security's written response confirmed awareness of the gap. It also confirmed that no emergency funding reallocation had been approved. The sirens worked. The sirens simply did not have enough time. Greenland does not exist in a vacuum. That is the part that is difficult to hold on to. The same warming ocean currents destabilizing Jakobshavn are pushing warm water beneath Antarctica's Thwaites Glacier on the other side of the planet. The same jet stream disruption sending atmospheric heat toward the Arctic is connected to extreme weather patterns across Europe, North America, and Asia. The same carbon dioxide concentrations, now approaching 425 parts per million, represent the closest this atmosphere has been to the greenhouse conditions that once turned Antarctica into a tropical forest and submerged shorelines that billions of people today call home. These are not separate emergencies operating on parallel tracks. They are the same emergency, showing up in different places at the same time. The 1958 Lituya Bay megatsunami in Alaska remains the largest wave event ever recorded. A rockslide triggered a wave that climbed 1,720 feet up the surrounding hillside. 5 people died because almost no one lived nearby. The Jakobshavn event produced a fraction of that wave height, but struck coastlines holding thousands of residents across several countries. The line between a geological footnote and a civilizational event is not the size of the wave. It is the number of people standing where the water goes, and the number of people living within reach of glacial coastlines is not shrinking. The international political response moved through its familiar stages. Emergency sessions at the United Nations Environment Program convened within 2 weeks. Iceland, Canada, and Denmark submitted a joint resolution requesting faster funding for Arctic monitoring infrastructure. It passed with wide support and a 3-year implementation schedule. 3 years is also roughly how long researchers estimate before Jakobshavn's newly exposed calving front stabilizes enough to evaluate the next phase of structural risk. The most widely circulated assessment in the weeks following the event came from a researcher at the Arctic University of Norway. His conclusion did not reach for dramatic language. It did not need to. He wrote that the Jakobshavn collapse had moved the most conservative end of sea level rise projections measurably toward the aggressive end. The range of scientific disagreement had narrowed in the wrong direction. Current atmospheric carbon levels are climbing at roughly 2.5 parts per million per year. The pledges made under the Paris Agreement, if fully honored by every participating nation, reduce that rate. They do not stop it. The ice does not negotiate with pledges. It responds to temperature, and the temperature, as every data set collected from Greenland's coastline in the past decade confirms, has been moving faster than the agreements designed to slow it down. The gap between those two speeds is where the next collapse is building. The fracture line is still there. It did not vanish when the water pulled back. It shifted. Jakobshavn's newly exposed calving front is now in direct contact with the same warm Atlantic water that carved out the hollow chambers that caused the original failure. The process that took decades to reach that breaking point is now working on fresh, unprotected ice. The glacier does not pause for budget cycles or legislative sessions or the findings of emergency committee reviews. It responds to temperature, and the temperature is not falling. In Kekrtarssuaq, the fisherman's boat was recovered from the coastal road and put back in the water 3 weeks after the surge. The harbor master building is still a concrete shell. The fish processing facility has no confirmed reopening timeline. He heads out every morning because the sea is still there and the fish are still there and his family still needs to eat. He does not say much about what he watched from the hillside, but he reads the water differently now. Everyone on that coastline does. That shift, the moment when an abstract scientific projection becomes something a person can feel without any instrument, is where the real weight of this story lives. Not in the parts per million or the annual millimeters of sea level increase, though those figures carry enormous consequence. In the harbor that empties before anyone understands what that means. In the 6-minute gap between what a warning system can deliver and what a community actually needs. In the 3 people still unaccounted for a week after an event that the official record will call a near miss. The ice fractured, the wave moved, the coastlines took the hit, and the world scrolled to the next story. But Greenland's ice sheet is still moving, quietly, continuously, and now measurably faster than the morning before the collapse. The question scientists have not been able to answer yet is which section of that glacier reaches its own limit next. The question the rest of us need to answer is whether anything will be different when it does.